At this point, the laptop has connected, but I haven't loaded any web pages. I've transferred virtually no data packets, just DHCP, I guess. And the correct card is a Broadcom mini PCI card. It's built in, and it's 3 down in this list. So I'm going to go over here, load some web pages, click reload a few times. Watch it jump to the top of the list. So give it enough data, it gets it right. And keep doing it, score gets a little higher. So there you go, real-time demo of fingerprinting. If we have time later, we'll do some people in the audience. Thank you. Okay.
We're running a little short on time, so this is going to be pretty quick. So finding exploits in device drivers. Finding exploits in device drivers is really what inspired this. And I got to be honest, Mr. Johnny Cash over here is one of the people who initially introduced me to this, because for the last, hold on a second. Sorry about that. For the last year or so, I've been looking at different kinds of device driver problems. And one of the things I really always wanted to look at was Wi-Fi stuff, but there were some problems with that, like how to do certain raw packet injection and things like that, modifications to code. So John is actually one of the people who got me initially started on that. So ways to find bugs, this is all your standard stuff. You got your static auditing, that's your binary analysis. You bust out your Halvar Flake skills and things like that. For open source stuff or things that come with it, source code analysis. One of the things that I found is a lot of people will reverse engineer binary drivers, then re-implement the way that they work in open source. So if you're kind of confused on how something's working, taking a look at the way the open source driver is doing it, for instance, like one of the Broadcom chips is pretty useful. And of course, one of the ways that we found a lot of this stuff was fuzzing. We will fuzz your built-in wireless cards, your third-party cards. We haven't done this much yet, but we want to take a look at the embedded devices and access points. John has had some success with making access points just not working anymore. Of course, that's not that useful, but it's pretty cool. So fuzzing can be frustrating, and if you ever had to hunt down a bug in ring 0 or basically in your kernel space, you can know that, man, that's not all that easy. I mean, it can be triggered by something 8 packets ago, and it's taking a timer or the timeout or something, then causing a crash or something like that. And for a lot of things, auditing or debugging in ring 0 isn't all that easy. Although, if you want to know more, I recommend the Barnaby Jack paper on stepping into ring 0 for the exploitation stuff. So this is actually John's slide. So.
Okay, fuzzy in like a minute. So fuzzy is my very uncreatively named 802.11 fuzzer. I still have your name, my fingerprinter, by the way. So this is fuzzy. Fuzzy has 3 interfaces. It's got an Ethernet interface, a fuzzing traffic interface to reject packets, and a monitoring interface. In this case, ATHO is monitoring. Fuzzing is on an RA-Link card. Basically, this isn't the kind of fuzzer that you run and like, bam, you get a crash. Fuzzy isn't very smart. It makes up for its lack of smarts in time. It's sort of like brute forcing the 802.11 packet space in some sense. So fuzzy is just going to create a packet with enough of a header that it looks like it knows where it's going, and then it's just random junk. Like, it doesn't make any attempt to try to make the type or subtype really look like a real subtype. It doesn't put any payloads in. There's just junk that looks like it knows where it's going. So it sends out all these packets, but first, before it sends the packets out, it pings the wired side of the computer it's attacking. Is it up? Great, let's throw some junk 802.11 packets at it. Okay, is it still up? Oh, damn, still up, okay. Well, I'm gonna move on to the next guy, because that guy's gotta recover. Because actually, the name of this game is getting as many packets out in the smallest amount of time as you can, and if you just fuzz the driver for like a minute, it takes it like 30 seconds to get back up to like, okay, I can transmit data again. So while it's getting up, it moves on to the next guy. And the next guy, okay, ping it, it's up, send some packets. Is it still up? No, great. Log everything I just captured off ATHO to a PCAP file and put an entry in a log file and keep doing this all night. So wake up in the morning, if you're lucky, all your laptops have crashed and you've got the Microsoft, your Windows system has incurred, seen a serious error. Would you like to send it off? Not so much. And there you go. That's how fuzzy works. Not very smart. Gets the job done.
And here's basically a screen detailing, you know, the command line options. It's pretty cool. So I wrote a fuzzer that works a little bit differently, and my fuzzer's a little bit, say again? Yeah, it's a little bit smarter. So basically what I do is reverse engineer driver a little bit to understand the differences between the implementations, and then implement the fuzzer based on that. Everything's basically, you write pseudo rules kind of like snort, and it allows you to add new packet types relatively quickly to exercise, you know, the kind of code paths you're trying to hit. So shellcode, one of the things to keep in mind about these types of attacks is normally, if you're going to exploit something and you get it good, you really can't get a connect back shell back to you. So you have the ability to attack machines that aren't on your same network, that aren't associated with the same access point as you are. So you don't really have that great way to do, you know, bidirectional TCP communication. So, you know, for most of these attacks, return shell just really isn't all that feasible. So these are really great for more like dropping a bot on a machine, or, you know, something that when a interface comes back up, it will communicate with you. But, you know, you're not trying to get a return shell initially. So we're going to run a video now that's going to show an interesting. It's going to actually show our interesting demo. We're running the video because we couldn't come up with a good way to to attack one laptop from another one without all you great people running sniffers getting copies of it. So we might have a slight problem with the sound, so I might have to narrate, and I have to tell you, I like kung fu movies. Device Drivers. Don't Build a House on a Shaky Foundation by Johnny Cash and David Maynor. Well, apparently it's not working, so right now I'm babbling about something I'm pretty sure. Something that we wish we could be doing live in Vegas, but due to security reasons, we can't really. So what I'm going to be doing is I'm going to be using this machine as an attacker, and I'm going to be bringing in another machine. Bam. That we'll be using as the victim. And don't think, however, just because we're attacking an Apple, the flaw itself is in an Apple. We're actually using a third-party wireless card. It's being obscured. So normally for this attack to work, you do not have to have the victim associated to an access point or authenticated in any way. But for the ease of this demo, this machine will, this Dell will be acting as a wireless access point with the address of 192.168.1.1, and this machine will have a address of 192.168.1.50. The attack will be launched from here. It will manipulate buggy code and device driver on this Apple. This Apple will connect back to the attacker with the shell, at which time I'll have complete interactive access. Don't I look constipated? Setting this up. The first part is turning this laptop into an access point. I do that with a script I wrote called setup. Making me a script kitty. We'll actually create an access point called SW Apple Demo. And we'll make this a wireless access point, and then we will connect the Apple to it. So let's run that script. No actual Apple icons were harmed in filming this video. We have an IP address of 192.168.1.50. Now what we do is we run the exploit. I have sexy fingers. This is actually what it looks like. This is the help screen for it. And now we will run it against the target machine. It takes a minute or two to run. It's preparing the shellcode for return. It's getting the connection information for this laptop. It's now sending the attack. That's where I pray it works. Response. It got a shell. Now, I am interactively logged into this machine. Let's minimize this window so you can see what I'm doing. I'm looking at the files in that home directory. So what I'm going to do first is create a file on the desktop called owned, O-W-N-E-D.txt. Wow. See, it was created right there.
And
Can't leave that
now,
laying around.
I'm going to delete it.
People might know their own.
Further proof, we can open a shell, and we can, onto the desktop, we can create a file called password. And in the file, I'm putting this is a secret password, exclamation point. I like to use exclamation points as it's actually secret. There it is created on the desktop. We're coming back over here. There it is, cat password. This is a secret password. And now, we will delete it.
And it's gone. I like to point out
This
that's not
concludes our
actually my
presentation. But if you're still not convinced,
I'm walking. I need to. Look how fat I am.
there are no wires attaching the two devices. I just create a file on the desktop called iwalkedaround.txt.
Showing on.
Yep.
And I just deleted it. The thing to keep in mind here is although we attacked an Apple, the flaw is not specifically in the Apple operating system as we use third-party hardware. This type of a flaw will be systemic across all operating systems and hardware, and the only way to prevent it is proper testing. Although this flaw is and can lead to a remotely exploitable condition, it's not as trivial as a generic buffer overflow. On behalf of Johnny Cash, myself, David Maynor, and the Security Research team, thank you for watching.
Seriously, didn't it look like I was a deer caught in headlights or something? So there's something I really want to point out. I own a Mac. In fact, the Black Mac Book Pro we were using was my actual MacBook. So we don't dislike Mac, or we're not trying to pick on Mac, or we're not trying to bash Mac. I'm actually a big fan of Mac. But we wanted to do some other demos, and they weren't panning out. So we thought, what could we go for that a lot of people wouldn't think that you could actually be able to break into. And I got to be honest, those Mac commercials, they just they jump right out at you. So we're not specifically targeting Mac. The thing to keep in mind is these kind of vulnerabilities are systemic across basically operating systems and hardware. I mean, and the purpose of a talk like this is to highlight that, yes, this is a problem, and vendors should be dealing with it now before it's a big problem in a year or two. So with that being said, do we have any questions? Do we have anyone sad they didn't get a copy of the exploit? Yes, sir.
In your experience, what percentage of these exploits end up in a crash, and what percentage of them end up in a
Well, what's funny is it's a very high crash to exploitable ratio. I mean, there's lots of conditions in a wireless stack that you can lead to a blue screen, but that's not going to be able to lead to an exploitable condition. Things just like you declaring that a certain amount of data will follow this, and it doesn't follow. Stuff like that. So there's actually a lot more DOSes than exploitable conditions, but I didn't think that showcasing a DOS on stage would have the same kind of punch. Yes, sir, in the back. The video is going to be posted on Brian Krebs' blog at washingtonpost.com/securityfix. So you'll be able to download it and scrutinize it until your heart's content. Or you can make fan pictures of me. I'm partial to that myself. Any other questions?